Hi, today I'll show you how to use AnDAPT's web-based tool WebAmP to build your own power management solution. We'll start by clicking on the Projects menu item and create a project. Once we create a project, we'll select the expected input voltage on the system. If you're not sure about the input voltage or it's subject to change, you can always come back and change it later. The current input voltage range is 4.75 volts to 20 volts. The next step is to select the platform. We'll go ahead with the most recent platform release, Platform B, and further select the 6-amp MOSFET family. Followed by the package size. There's 5x5 and 8x8 package sizes. I'll select 5x5 on this one. The design view block diagram is the basic platform with 8 power blocks, each containing a MOSFET and embedded drivers. We have 2 fixed LDOs, a 1.2 volts LDO and a 3.3 volt LDO, each capable of delivering up to 200 milliamps. Additionally, we have 2 programmable LDOs, which can be set to different voltages or enabled or disabled, and they can also be sequenced with other power rails on the system. In addition, there is an OTP block that can be used to inform the system that the part has a thermal shutdown. The signal can be brought out on any of the GPIO pins. There's an onboard clock on the IC. The silicon has 2 oscillators, A and B, each ranging from 500 kilohertz up to 32 megahertz. These clocks can be divided into several number of phases. For example, right now 7 phases are selected, dividing the 4 megahertz clock to 571 kilohertz. You can just as easily bring an external clock from a GPIO or do a different divide ratio. Different phasing can be selected for the clocks. Continuing back to the design view block diagram, there are 24 different GPIOs on this 5x5 package, and all of these GPIOs can handle analog or digital signals as the user decides. On the left side, there's a constantly evolving library of different power components. These power components can range from different switchers and different topologies such as async buck, sync bucks, buck boost, or linear regulators, including LDOs, load switches, high current Dr. MOS controllers, single phase, dual phase, and supervisor tab includes sequencers and digital logic building blocks such as gates and clocks, etc. Next, we can grab one of these building blocks and try to build our own PMIC. Let's go with the synchronous buck. So the synchronous buck will consume 2 of the MOSFET power blocks. And as you can see that I've also dragged and dropped the external components along with the power component. Let's go ahead and select an LDO, which will consume 1 FET, and a sequencer. And let's go ahead and select 1 single phase Dr. MOS. As you can see, when I dragged and dropped the Dr. MOS controller, it also dropped the external Dr. MOS IC. You can connect different enable pins to either GPIOs or to the sequencer in a way your power solution demands. Let's jump into one of these PWM sync converters. As you can see on the left-hand side, there's different knobs that are available to configure your device. They range from switching frequency to input voltages, output overshoot, output current, ripple. So right now, we've selected 571 kilohertz as the switching frequency for this buck converter, but we can go ahead and change if we desire that in the clock. We can select a different input voltage and an output voltage. As I select a different output voltage, the tool is smart enough to change all the fault values to an appropriate number. I can select the output overshoot and the ripple as well. Let's say 45%. As I select a different output ripple, the tool predicts an inductor, or it suggests an inductor size that would be appropriate for the application. However, it may not be a standard size. For this application, we have incorporated an inbuilt BOM tool, which scrapes Worth website for the available standard sizes. If I click Worth, it'll show me different inductor sizes in the vicinity of the selected number. Takes a few seconds. As you can see, I had selected a 1.3 mic, but in the vicinity, you can see there's a whole range of different inductors available. In addition, there's different parameters based on which you can make a selection, including DCR, saturation current, the size of the inductor. Different data sheets are embedded here. You can click on the PDF icon here to get the data sheets, and you can get free samples, etc., etc. I'll go ahead and select 1.2 microhenries. And as you can see, that my ripple is calculated using the inductor that was just selected. In the same way, the user can select the capacitor from the BOM tool as well. Following this, the user has the capability of changing the controller and the dynamics of the synchronous buck converter, which leads up to the second tab, which is the Buddy plot tab. This is the default Buddy plot. And as you select the inductor and the capacitor, you can see that you have a specific phase margin and a crossover frequency. If you want to tune the controller for your specific needs for certain bandwidth or stability, then you can use this icon to change the gain or change the position of the poles and zeros. Or you can either change FC1, FC2, and gain in the left-hand side to tweak the controller. Moving on, the fault protections are standard and are provided in the tool, include input and output UVLO, OCP, OVP, and other constraints such as soft start and power good. So once the inductor is selected, we've correlated with bench data and this GUI tool efficiency plots so that the user can predict what the efficiency is going to be for the system and the chip loss as well. And here, if you don't like it, then you can go to the click this Worth icon and select another inductor and see how your efficiency is going to change for a different selection. As you can see, not a lot of tools provide AC losses, but we've incorporated them using Worth data in this tool. Going back to the design tab. So we have these tools available for all our other power components, including LDOs, Dr. Moss, et cetera, et cetera. I'm going to jump ahead and open a design example that I constructed earlier. Let's not save this. As you can see, this design example has been created beforehand and all the connections have been made. One thing I wanted to point out was that each component that you select, or you want to know more, there's a PDF icon to the left of it, which has a data sheet for that component, and you can learn more about it. So in this completed design, you can explore more about the thermal performance of your device using this thermal tab. You can punch in the TDC of different power components, how much thermal design current your part is expected, or each rail is expected to deliver, and then you can predict what the chip loss is going to be. So if I go here like 2 amps, There's an auto datasheet generator. Once you click it, it generates an auto datasheet for your custom part. A new datasheet will be generated for the custom part, which is right now. Let's save it and open it. Just take a quick look at this. So this custom datasheet will have the details about the base silicon and also about the application specific device that you've just generated, including the details of the rails that we just created, including 2 sync bucks, 1 async buck, 2 LDOs. Other details include the pinouts and the physical package picture, the thermal view, and details about each of the part components, and the BOM, and other details. The next step in creating the PMIC is compilation. So once we compile, this part is compiled on AWS, where these last 3 files are of interest to the customers, which are the Intel hex file, so that they can program their flash, our own hex file, HAX, which is used to program the AMP part, and the bill of material with all the components selected in the BOM tab in one CSV file. Here the compilation is finished, and it shows some resource allocation on the device, how many LUTs are consumed, etc., etc. The compilation time is 49 seconds. Next step is the AMP link, which is our gateway to programming the part. Here, the user can select the part or the flash, and then they can program and verify the device. If you do not like something at this end, you can go back and repeat the process, take a couple of more minutes. Then finally, you can control the device from the control panel here. That finishes the tutorial for WebAmP. Thank you for your time. Please feel free to ask any questions.